Hello and welcome to Physics Online. This is Teacher Patrick and I just want to welcome you to today's lesson. If you have any question, leave a post. So today we will be looking at resistance and resistivity. At the end of this week you should be able to make the following connection. You should be able to define resistance and the ohm, recall and use V is equal to I times R, voltage is equal to current times resistance. You must be able to sketch and discuss the IV characteristics of a metallic conductor at constant temperature, a semiconductor diode and a filament lamp. You should also be able to state Ohm's law and recall the use of the resistivity formula where the resistance is equal to the resistivity, the length of the conductor divided by the area. Okay, now the word consciousness section, we're just going to look at a few words, make those light bulbs switch on. So the first words we just want to look at, what is resistance and where does it come from? Resistance comes from the Latin word resistere, sorry if my French pronunciation is wrong, and that means to hold back. Okay, ohm is a SI unit for electrical resistance. Metallic comes from the Greek metallion, which means to mine, to quarry, or metal. Okay, characteristics comes from the Greek word characteristikos, or a stamping tool. A conductor is from the Latin word conductere, which means to bring together. A diode is an early 20th century English word from die, one or two, plus a shortened form of electrode. And then we have lamps, which is Latin for lampus, lampad or torch, and filament, which is film, which is a Latin word for thread. Okay, so the IV characteristics, we're going to look at the IV characteristics and just make sure that we remember them from IG. Okay, so the next part here, firstly, what is an IV characteristic? IV characteristics are curves, which is short for current voltage characteristic curves, or simply IV curves of an electrical device or component. IV curves show the relationship between the current flowing through the electronic device and the force applied, or the voltage applied across its terminals. Okay, if we firstly look at a metallic conductor, this is now a conductor that obeys Ohm's law. First thing that we want to see is we want to see that we have current on the y-axis and voltage on the x-axis, hence the word IV, which, as you know, is the opposite of V over R, which is Ohm's law. So the gradient of this line is the resistance, and hence if we look at the VI ratio is constant, that tells us that there is constant resistance. This is an ohmic conductor. This is a conductor that does not gain heat. The next one is for a non-ohmic conductor, like a lamp. As we all know, the longer you have a light switched on, the warmer it would get. Okay, so in a non-ohmic resistor, as the voltage increases, so does the temperature, and therefore the resistance increases. Hence, it does not follow Ohm's law. The word non-ohmic refers to that, because the resistance increases and the temperature changes. Okay, the next one we'll look at is a thermistor. Now, a thermistor is a device that measures temperature. Okay, and it's used in a lot of places, like heating system warnings in a car, or an aeroplane wings where they have to get warnings when the wings start freezing. So this is a type of electrical component that is sensitive to temperature. Now what happens here is opposite to the ohmic resistor. As the voltage increases, the temperature increases, but as the temperature increases, its resistance decreases. So in other words, when it's hot, it allows for current to flow faster. We can see that the curve is increasing in gradient, meaning the resistance is decreasing. Remember, we said that the resistance is opposite to the gradient. Okay, the next one we'll look at is the semiconductor diode. And the semiconductor diode is a component that specifically prevents current to flow in the opposite direction. This is used when we turn alternating current into direct current. Okay, so what we see is that it has a load resistance in one direction and an infinite the resistance in the opposite direction. So the opposite direction is the negative voltage side. There is infinite resistance, meaning there is no flow of current. The low resistance on the one side is now in the positive quadrant that we see here, and we see that the gradient is increasing, hence the resistance decreases the bigger the voltage gets. Okay. Resistivity. The resistivity of a material is numerically equal to the resistance of a 1 meter length of the material with a cross-sectional area of 1 meter. As you can see in the diagram below, the electrons are actually flowing through the metal as the current pushes them through the conductor. These electrons bump into the positive atoms that's left with the delocalized electrons moving, okay, and they have to squeeze past, and the more difficult their flow is, the bigger the resistivity will be. Resistivity is a property of a specific metal and therefore changes when we move from one material to another. Okay, so resistivity is dependent on three things: the resistance, the cross-sectional area, basically the thickness, and the length of the resistor. Now, we know that the resistivity formula comes from this formula where we say that R is the resistance of the material, is equal to rho, Greek alphabet letter rho, which is the resistivity of the metal, L, which is the length of the resistor, and A, which is the area. So here we can see that the resistivity would be, okay, directly proportional to the area and the resistance, and inversely proportional to the length. And if you're not sure how I got to that, you would be able to do that if you rearrange the formula. Okay, so that concludes resistivity, and I hope that there is no problems anymore with your understanding on resistivity. I hope you have an awesome day, and please, if you have questions, leave it in the post below.